It's a pleasure to be the first MP fodder that's going to put your lights out. So Andrew set the stage perfectly earlier today when he spoke about genomics and how genomics is changing everything in healthcare and agriculture and even as we think about computer technology. It's changing so much that we've got a really big problem. Nature estimates that by 2025, 2 billion genomes are going to be sequenced. That means that there's going to be 40 exabytes or 40,000 petabytes of data produced annually. That's a massive amount of data. That's more than YouTube and Twitter produce. They produce only 200 petabytes annually. So this is 40,000 petabytes. This is a massive amount of data. And so this is a big problem. So what do we do about that? So generating petabytes of genomic data is not the only trend that's going on in the marketplace. There's also been big shifts in big data analytics and big data software. There have also been big shifts in what's been happening with extreme scale IT. And we believe one of our first left turns is, and having spent 2 decades in the tech industry, that if you look to the intersection of these technologies, you can start finding the answers for new insights, accelerating research, generating new cures, and ultimately enabling us to live longer lives. When we look into sequencing, there is a defined flow that sequencing goes through. You have to prep the samples. This is a biological thing. Then you actually sequence it, like we spoke of earlier today. Then there's a lot of data processing that goes on, aligning the data, secondary analysis, and then deriving what that information means. Well, there's been an interesting shift. It used to be that the vast majority of the time and complexity was in the sequencing, which of course we had our discussion about. Today, it's about 50-50 between the time we spend sequencing and then the time we spend actually trying to understand what the sequencing is telling us. But where this is going is that the sequencing is getting incredibly cheap and getting a lot easier and getting more repeatable, which is what's enabling us to get to 2 billion genomes sequenced. But the data processing is an enormous challenge, and it's replacing the challenge of sequencing. It's changing it so much that when we analyze genomic data, and just due to some of the inefficiencies of the way the processing happens, there's a 3 to 5x expansion of the data while we're processing it. So there's not only going to be 40 exabytes of data produced annually, there'll be over 120 exabytes of data produced annually. So this is a really big problem. The way the industry handled this prior to this was they would throw high-performance computing clusters at it. It sounds like a powerful solution, doesn't it? That should be the answer. Throw an HPC cluster at it. But that's not the way it should be done, because high-performance computing is about compute. And there's a problem there, because this is about genomics data, and there's a lot of data. So we need to look to other technologies like Hadoop. And this is where we found our first left turn, was in recognizing that with HPC, you've got centralized data in one separate system, you've got compute in another separate system, then you've got a network that you hope is fast enough and big enough between it, and that ends up in lots of bottlenecks between. And so, but this doesn't work, because bioinformatics is big data, and you've got to combine that with compute to get that done. So in genomics, the data is too big to move. So what you need to do, and this is our big idea, is to move the compute to the data. And that's what we've done. So we've dropped in a system that is based on big data architecture that combines compute and the data together in one system with the genomic analysis capabilities and the data management together with extreme scale IT, so that you get the scalability, you get the performance, you get the data management and the genomic analysis on that foundation. We've also combined that with the downstream analysis capabilities so that you can get all the deep, richer insights, looking at disease causes and finding the meaning behind what's inside of that data. And this is relevant for things like doing family studies on rare and inherited diseases, looking at cancer for tumor versus normal, or as much as the case these days is cancer versus cancer, looking at the mutations, and looking at populations of studies. Even more so when you put this into a big data construct and you look across multiple causes of disease, and then you look, those are what we call phenotypes, and then you look at that across the millions of genomic variants, you can actually start getting to new insights and find the relationship in disease and mutation causality. And that's what we've done. With that, I just want to end on a note of thanking the team that's made this all possible and turn it over to the next.